But certainly it is dumping a lot of pollutants such as lead, cadmium and arsenic into the streets and onto the buildings of Seoul, which of course all gets washed down again in rainstorms, gets into the Han River and then gets dumped back into the Yellow Sea. Now, we can't go very far in earth science without talking about ages. And the rocks that are coming around have actually been dated, or at least the minerals in them have been dated by radiometric means, and I won't go into that in detail, but that is a method, an isotopic method, which can give you a precise or an absolute geological age in terms of millions of years. If we take a look at the minerals from the gneiss, we find that they are an incredibly old age. They are between 1,800 and 2,500 million years old. In fact, they're the oldest rocks in Korea. Very old indeed. There's of course a bit of a slop on that, but essentially they belong to one period of geological time called the Precambrian. Then you've got a long period where there's just absolutely no rock representatives at all until you get to the granite. And the granite is much younger, but it's still 165 plus or minus 5 million years. And then you have to go another long way forward in geological time before we start seeing the time when the river gravels were being deposited, and that was about 1.8 million years ago. So we have these three different rock formations, if you like, of very different ages in geological time. Some, the gneiss, it being the oldest in Korea, and it's the gneiss, in fact, that at some stage, perhaps close to the age of the granite, it started to melt. In fact, the granite is derived from the melting of this early Precambrian gneiss. And on this side, there's, I guess, the geological time scale, which you don't have to pay much attention to, but all these absolute ages from all over the world is divided geological time up into these periods and epochs, and of course you know the Jurassic, where the dinosaurs were, and the dinosaurs all died out, but the Cretaceous, a little bit younger than the formation of the granite that makes up Seoul, or most of Seoul. So those are the ages. If we go into a little more detail, well, I told you before that the granite is a molten rock. At one stage it was a liquid, and then it started to cool and crystallize the various minerals that you can see in it. And if you separate out the individual minerals in one particular granite, in this case the Seoul granite, and you date those individual minerals, and you know the closure temperature, approximate closure temperature at which that isotopic clock stopped for individual minerals, then you can plot this relationship between temperature and degrees centigrade and age in millions of years. And so the first mineral that crystallized from the granite was, say, 172.3 million years old, and it's crystallized out when the temperature of the granite had decreased to just a little under 700 degrees. And then as the granite slowly began to crystallize and different minerals crystallized out, and by the time you got to the last one, you're looking at a temperature of 300 degrees, when the granite would have been essentially a solid rock, but still hot at depth. And that formed at about 145 million years ago. So that piece of granite that's coming around for you to have a look at took from 172 to about 145 million years to crystallize as a solid rock. So the age that I gave you before, of about 165, is an aggregate, if you like, of all of those ages together. And then, of course, you need to extrapolate the cooling curve down in the way that I've done it to present-day ambient temperature. And that, of course, that final cooling took place from 145 million years ago, I guess, until almost now, when the granite became exposed. But if you take a simple line through those age-dated points, then you're looking at a cooling rate somewhere at a depth of about 14 or 15 kilometers below the surface, of 14.5, 15 degrees centigrade per million years. So it just shows you that it takes a long time to form the rock, but nevertheless, in terms of our whole geological time, with the oldest rocks being 2,500 million years, this is nothing. It's a very short time indeed. So I guess this is a kind of a very crude reconstruction of what we're looking at today. We're looking at a granite which resulted from the heating up and the melting of the metamorphic gneiss rocks, which are there in purple. And that granite must have formed, we know from different minerals and pressure indicators, that it formed at least 14 or 15 kilometers below the surface 165 or 170 million years ago. So all of the rock above that is completely removed. There is no rock, no evidence of that rock at all in the Seoul Metropolitan area. There is outside the Seoul Metropolitan area, there are bits and pieces still preserved, but in the area we're talking about, it's all gone. So at least 10 kilometers or more of rock has been stripped off the top to expose the granite and the metamorphic rocks, and that wiggly yellow line is just a crude approximation of the topography of Seoul, so that some places we're getting granite exposed, and other places we're getting the metamorphic rocks, the gneiss is exposed, as you saw in that initial geological map. Now, the granite. Here are some pictures of around Seoul and the high mountains showing the granite. You can see that a lot of that is just bald rock faces. No vegetation on there at all. Smooth, steeply dipping faces. And the form of the granite is that they look like a whole lot of domes. They've got a dome-like appearance, as you can see. And the reason for that is because the granite, like the metamorphic rock, is transected by a number of joints. Two vertical joints at right angles, and another set of joints that are much shallower dipping than the vertical one. So it breaks the granite up into kind of blocks or cubes. So that if I now have a look, for example, at Mount Bukan there, and I can see a series of lines like that. Those lines are the joint planes I'm talking about, and then I can put them in like that. So these are all major joint planes, and they of course control the erosion of the granite over time, and that produces the particular form of all the granite mountains. That's only one set of joints. There's another set of joints at right angles to that are also fairly steeply dipping, and there's yet another set of joints which are much more shallowly dipping that go over the top and in fact curve over the sides of these domes. And if we look at this one here, again, I can put on some more joint planes, and there you can see the more gently dipping ones like that, and of course those flattish, smooth faces down the side of the granite there are also joint planes. So clearly the topography and the form of the granite mountains and the dome-like shape is controlled by these joints. These joints are inherent in the rock, and they're caused by the cooling. They're contractional joints. When the granite cooled down, presumably below 300 odd degrees, it contracted, and then it formed. Because it's fairly uniform in the grain size, as you will see when it comes around, the granite had this cuboid or block-like jointing pattern all through it, everywhere. And so, consequently, the mountains are all the same kind of shape. There are variations, of course, and some, of course, as you can see here, dependent upon the arrangement and the number of joints, or the close space of the nature of those joints. If we go to one particular area, Insubong, which is located here, you see there's a series of joints coming down like this, but there's clearly slabs of rock that have broken off and slid away from the steep parts. And if we take a look at this, I guess, diagrammatic picture here, we're looking at one set of vertical joints and another set of curved joints, which are essentially controlling the slope of the granite. And here we've got four blocks divided up into the original joints with time. And then we have certain blocks that are removed because these blocks are tilted, so there is a slope, so under gravity this stuff will move. And gradually you can see how with time the granite changes from its cuboidal form here and gets a kind of a bit of a topography with time.